Hey class, it's Professor Rourke. I wanted to make another video from 7.4, the partial fractions section of our textbook. And this number 7 is a doozy. So it it's it's got some painful parts in here. Particularly with the fractions, I want to say really kind of takes the cake here. But it's got some different things. So because this is such a lengthy problem, I'm going to add some timestamps so that if there's a certain part of the problem that you feel comfortable about, you can jump to the next part of the problem. Okay, so the integral that we're looking at here is 29 divided by the quantity x cubed minus 125 dx. Okay, so some things we want to notice, right, is we just have this random number 29, which isn't going to help us today, but that's okay. And we also have x cubed minus 125 in the denominator. All right, so let me first of all, I'm going to go ahead and just pull the 29 out because in front of the integral because we have enough to worry about. And then it becomes a problem of trying to figure out how to possibly integrate something like 1 over x cubed minus 125. So first things first, hopefully we're sort of thinking partial fractions because we don't have any methods to just approach this problem. Otherwise, we just don't. We could possibly use like the table of integrals, which we started looking at in 7.6, but before now, this does not fit any type of trig substitution. It doesn't follow integration by parts. U sub wouldn't work. It's not looking good. Okay, so we are going to first begin with partial fractions. So the textbook has a few different ways of explaining it in the help problems, but we're going to mostly attack these the same every time. And what we all will want to do to start out with is let's just go ahead and pull off to the side 1 over x cubed minus 125. Okay, this is what I'm going to focus on, just rewriting using partial fractions. So x cubed minus 125, that is a difference of perfect cubes, which does factor into like whatever is like a minus b times a squared. So we'll say x squared. Then the next sign is the same. It's always the opposite. So it'd be x squared plus AB. So we'll say like 5x and then plus 25. Okay, so I hope that that's okay. All right, that's just how we have to factor this difference of perfect cubes. So from here, the whole idea is that we want to try to use partial fractions to try to figure out what would the coefficients have been to have like, it's like the reverse of getting a common denominator. Okay, so we'll say like a divided by x minus 5 because that's a linear factor. Okay, but the x squared plus 5x plus 25, that's an example of the, like it's simply you can't factor this quadratic denominator. So we have to use bx plus c. Okay, and it doesn't repeat, so I guess that's something to be somewhat thankful for. And so now we have to solve for a, b, and z. So this again is the first hump in this particular problem because this is what we have to first tackle. So we're going to go ahead and clear the fractions out. And we clear the fractions out by multiplying by the denominator. We're left with just 1 on the left-hand side of the equation. And then the right-hand side of the equation, we're left with a times x squared plus 5x plus 25. And then plus, we'll just, again, take it nice and slow, hopefully. We have the quantity bx plus c times x minus 5. So you might see a few different ways of solving these partial fractions if you look even within some of the ways that our textbook provides solutions is a little different. There are a couple of shortcuts you can try, but we're not really messing with those, okay? We're just using partial fractions as a means to an end, okay? And so we're not gonna get into different methods, but if you feel comfortable to try those, you're more than welcome to. Okay, so I went ahead and expanded this out. So I have ax squared plus 5ax plus 25a plus bx squared minus 5bx plus cx minus 5c. Okay, so just again, just expanding. And the whole reason we do that is because first I'm going to go ahead and like group these. This is an optional step, but I just want to make sure we're all on the same page. So I'm going to group like the x squared terms together, and then I'm going to group the x terms together. Okay, just literally next to each other. Okay. And then, so I have ax squared plus bx squared. Those are my x squared terms. Then I have 5ax minus 5bx plus cx. And then lastly, I have my terms that don't have an x. So there's all kinds of ways of organizing these particular questions. I like, it's up to you. Okay, how you want to do this. You can put parentheses around these if you like to. Okay. And then the whole idea is that we are going to now set these coefficients equal to their corresponding terms on the other side of the equation. So if I were to factor out an x squared, I'd be left with a plus b. If I was to factor out an x, I'd be left with 5a minus 5b plus c. And then I don't have any x's in my last term. So I'm just going to say 25a minus 5c. And the reason we did that is so that we could set these coefficients equal to each other. So I don't have an x squared term. I also don't have an x term, and my constant term is 1. So let's see what we have here. So we're going to say a plus b for my x squared terms equals 0. We also can say 5a minus 5b plus c equals 0. And then I have 25a minus 5c equals 1. Okay, so from here, we have some options of how we can solve this. This is a system of equations with 3 variables and 3 unknowns, right? 3 equations. So we, I think that as of right now, because this problem is so involved, you can pick whichever method works best for you, but I'm going to go ahead and show you just how to use the graphing calculator using RREF so that hopefully it's as quick as possible. Okay, let's see here. All right, so I have my graphing calculator at the ready. Let's go ahead and share this. I think my whiteboard went away. We'll bring it back. Okay, so for this particular problem, let me go and get my whiteboard up real quick. I'm going to enter my data on my calculator off to the side. Okay, so we are going to, again, go to the matrix, and then we are going to enter in this data. So this particular matrix that we have, this is a 3-row by 4-column matrix. Okay, it's technically what we would refer to as an augmented matrix, and that's not really essential. That's not going to be on the test, but it just, I know linear algebra goes into all these sorts of really cool methods of math that has been discovered where we can use just all sorts of matrix operations to find these values. We do not need to worry about the ins and outs of these systems of equations right now. Okay, it was really it's just one of the tools that we're going to use. Okay, so as long as you can go to your matrix and you can enter your data in correctly, you do need to make sure that you double check your numbers when you put them in, because it's easy to sort of go astray. And then let me go ahead and pull up out what we're going to do from here. Okay. So I have my data entered. I'm going to go back into the matrix. I'm going to go over to math, and I'm going to go to RREF. That's reduced row echelon form. Okay. Oops, I went to click the button too many times. So RREF, and then I'm going to recall matrix A. So I'm going to hit second x negative 1, which takes me to the matrix, and then I can see these lovely numbers here. Which those are something. So I can also do the math fraction option that we talked about before, okay, where it turns these numbers over into fractions. Okie dokie. So let's go ahead and go back to where we were before we started doing matrices. Okay, so this tells me that A equals 1 over 75, okay, B equals negative 1 over 75, and C equals negative 2 over 15. Okay, so that's something. That's a bit something we don't see often, is solving these systems of linear equations. That's a part of partial fractions that can be sort of challenging. Okie dokie. So once we have this, we're going to go ahead and substitute these values in for A, B, and C into what I had broken up here in my partial fraction composition. So let's give this a try. Okay, so also my microphone died, so I'll make sure that I talk loud. So hopefully you can hear me okay. Okay, so what we're going to do again, the whole reason we did all of that was so that we could get here and we could rewrite this original expression. Instead of saying a over x minus 5 plus bx plus c divided by x squared plus 5x plus 25, we are going to substitute in a is 1 over 75, b is negative 1 over 75, and c is negative 2 over 15. Okay, so just focusing again on the partial fractions, we're going to go ahead and rewrite this. I'll also put it back inside of the integral that we had written before, just to make sure we sort of understand what's going on here. Okay, so I'm going to write this as 1 over 75 divided by x minus 5. Okay, and then I will also go ahead and say plus, there is some ugly fractions coming in. Okay, just a heads up. Forewarning, but that's okay. We got this. So we have bx is negative 1 over 75x plus c, which is negative 2 over 15. I'm just going to leave it as negative 2 over 15 for right now, and then we'll come back and hopefully make this look a little bit nicer. Okay, divided by the x squared plus 5x plus 25 situation. Okay, so from here, what we want to do is we want to use some simplifying of fractions to make our lives a lot easier. Also, we're now essentially, we broke this up. The whole reason we did this was so that we could get it into two different radicals, two different integrals. So let's go ahead. I'll now also sort of distribute the 29 so that I don't have to worry about this later on down the road. Okay, so I got a little sidetracked by the children, but I hope this makes sense that I'm going to split it up into two radicals, and I also at the same time it makes sense to apply the 29 at this time. I just don't want to lose a 29 anywhere. Okay, the 29 has to be working on both of these, and I want to make sure I don't lose it. Okay, so what I'm going to do is I'm going to say 29. I'm also going to go ahead and pull out the 1 over 75 from the first integral. And then the second integral is a little bit more involved. So I want to make sure I go through that slowly. Okay. So I have 29 times, I pulled out the fraction of 1 over 75, and I have the integral of 1 over x minus 5 dx. Okay. That one, actually, I'm mostly done with that integral, even if it doesn't feel like it, because we're just going to use, we have an ugly fraction, we have natural log. It's the other fraction that can be a little tricky. Okay, so the moral of the story is that we can pull out, we can solve the problem of these really gross fractions, and it's not too bad. Okay, let's say I'm going to say plus 29, and then I'm going to have the integral for now, and then we'll talk about what we could possibly like pull out as a greatest common factor out of negative 1 over 75 and negative 2 over 15. Okay, if we pull out a negative 1 over 75, that would essentially like fix these really ugly fractions that we have right now. Okay, so I'm going to go ahead and pull out just inside this integral for now. I'm going to pull out negative 1 over 75. Okay, and then what I'm going to have left is negative 1 over 75x divided by negative 1 over 75x is just x. Okay, and then this is where we can use our graphing calculator if you need to think about this. But if we have negative 2 over 15, okay, divided by 1 over 75, we're essentially like multiplying by 75. Okay, because when we're dividing by a fraction, it's really like multiplying by the reciprocal. But again, also you can just put in your calculator here, negative 2 over 15, put that in parentheses, divided by 1 over 75. Okay, and I am pulling out a negative one, so
2 over 15, just to kind of like show it up here. I'm gonna say 2 over 15 just to show you, divided by 1 over 75 is the same thing as 2 over 15 times 75 over 1. Okay. And 75 and 15 can cancel out to give you 5. That's where we're going to get our 10 from. So I hope this makes sense in some regards, but I know, again, just the fractions alone can be sort of challenging. And then we'll talk about the next challenging part of this problem. Okay, so all of that comes down to, if I were to think about these two separate integrals, we have 29 divided by 75, which is a little rough, okay, times the integral of 1 over x minus 5 dx. And I'm also going to go ahead and rewrite this as minus 29 over 75 of the integral of x plus 10 divided by x squared plus 5x plus 25 dx. Okay, so that is what I need to do just for partial fractions alone. And it's not pretty, okay? Because again, we did have 3 unknowns, mostly because of this whole unfactorable quadratic. That is what makes this particularly a bit rough, okay? And then there's actually some painful parts from here as well. So the first step to solve this problem correctly is we need to make sure that we feel comfortable just with this alone, okay? Just being able to use partial fractions and using some fraction operations to be able to write this integral as 2 separate integrals. Yes, there's some ugly fractions involved, but also, you know, we've done worse before. Okay, and also if you take a look, we do have the same fraction of 29 over 75 for each of those. So that's something to be thankful for. So we could even like essentially pull out the 29 out of over 75 all the way back out to the front if we want to. It's sort of kind of up to you depending on if you feel like if you're concerned that you're gonna maybe like lose any of these numbers, then you know you don't want to. You would maybe want to keep the 29 out of 75 in front. If you feel pretty confident that you'll remember to then redistribute 29 out of 75, you can do that as well. Okay, so I'm going to go ahead and clear the screen out just for the partial fraction work so I can have a lot of space to talk about the next part of this problem. Okay, so something that we talked a little bit about when we were completing the 7.4 notes was that lovely completing the square situation. We haven't practiced it that much because it comes out of nowhere, it comes out of left field. But that is something that we're going to need to use because let's deal with one thing at a time. Okay, so we have our 29 out of 75 hanging out front. I'm just going to leave that there. Then next up, we have the integral of 1 over x minus 5 dx. This is one that you do want to feel comfortable about because it's helpful to know which ones, you know, are the hard work ones. And that is the integral of 1 over x minus 5 dx is just natural log of x minus 5. Okay, so I hope that kind of makes sense. The problem that we have actually is the x plus 10 divided by x squared plus 5x plus 25. Because there's some stuff wrong that makes things a little tricky here. We can't do like a simple u sub because what do we make u is what, x squared plus 5x plus 25. Then du would be like 2x plus 5. And we have x plus 10. So that doesn't really seem to help us out very much. So when we have this essentially like a linear term in the numerator and a quadratic term in the denominator, what we want to try to work towards is completing the square so that we could then break up this integral again further into maybe a piece that has a arctangent form and a piece that maybe does not. Okay. And again, I know that sounds excessive. Don't forget that when you're solving these, feel free to check your textbook. I know we like to go over as many examples as we can in class, but if you're feeling stuck, there's usually some kind of example that does correspond with what we're looking at. And again, this is a particularly tricky problem because we have this quadratic that's messing up our day with the partial fractions. Okay, so we did partial fractions and we come down and we still have something else left to do. So what we're going to do is I'm going to go to the side, and I'm going to focus on trying to complete the square, and then I'll bring this back, okay, into the fray. Sort of like how we treat things with when we're solving partial fractions, is like we kind of take the equation off to the side and then we bring it back in. Okay, so if I had something like, just a little side work here, x plus 10 divided by x squared plus 5x plus 25. What I want to do is I need to get the x squared plus 5x plus 25. I need to want to complete that square. Okay, so you can even go off further to the side if you'd like to. When we are completing the square, we focus on isolating like the x squared and the x term. Okay, and so I'm going to like boot out the 25 for right now, and I have to keep this all on one side of the equation. Okay, and then I need to figure out what I need to add to make this a perfect square trinomial. And this is why this particular problem is a little oomph, because 5 divided by 2 is 5 halves. And then we have to add, we have to square that and add that. Okay, so if you want to write that down, it's like b over 2 and then squared. It's not pretty. Okay, so that's 25 over 4 that I have to add inside my parentheses, and also to compensate, I need to subtract 25 over 4 from that 25 that I had put off to the side. So this is where things really start kind of the reason I did that was so that I could rewrite this as x plus 5 halves squared. And then I do need to simplify 25, take away 25 over 4. Okay, so again, you can use your graphing calculator if you're not a big fraction fan. However, this is essentially just comes down to like 100 minus 25 divided by 4. Okay, if we got a common denominator, which is going to leave us with 75 over 4. Okay, so, you know, all right, not the best vibes, but we got what we got. All right. So what I'm going to do is, instead of writing, I'm going to return back to this x plus 10 divided by x squared plus 5x plus 25 margin work. Instead of writing x squared plus 5x plus 25, I have to write x plus 5 halves squared plus 75 over 4. Things not great, but it's going to hopefully make some more sense very soon ish. Okay, told you the messenger. All right, so what we're going to do next is return to our lovely integral, okay, where we have like x plus 10 in the numerator, and then instead of writing x squared plus 25x plus 25, we're going to rewrite this as x plus 5 halves squared plus 75 over 4 dx. Now, why would you want to do that? Because we're actually going to break out a u substitution. We're going to say let u equal x plus 5 halves. Okay, this is what we're going to do every time we need to use the completing the square. So if u equals x plus 5 halves, du equals like 1 dx. So that's good. But also what's going to come into play is we need to solve for x. Okay, so this is a more complicated u sub that does require some effort. Okay, so instead of rewriting this, I'm just going to focus on this integral on the right hand side, and then I'll bring down the 29 times the natural log of x minus 5. Okay, once we're done with what we have going on here. So instead of x plus 10, I'm going to substitute in what u is in terms of x. Okay, so instead of, I'm going to write the integral of x plus 10, I'm going to insert u minus 5 halves plus 10. Okay, and then in the denominator, I'm going to go ahead and say this is a u squared plus, it's still a little rough. Okay, it's still 75 over 4. There's not really, unfortunately, too much we can do about that. But then, hey, the good news is that dx is just du. I don't have to make any compensations for that. Okay, so that's good. Okay, so now we're going to go ahead and simplify what u minus 5 halves plus 10 is. Right, if we had a common denominator, 10 would become 20 over 2. So it's negative 5 plus 20. So we're talking about like 15 over 4. Okay, and then divided by u squared plus 75 over 4. Okay, why would we do that? Because now that we have this written in this way, we can break this up into two different integrals. We can break this up into the integral of u divided by u squared plus 75 over 4. And we can also break du. We can also break it up into like minus 15 over 4 divided by u squared plus 75 over 4. Okay, why might you ask we do that? Because we can actually solve the first integral fairly easily using another u substitution. Okay, and then the integral on the right, we're going to bust out some arctan. Okay, so I know it doesn't feel like it, but we're almost done. Okay, so I'm going to say, I don't know, I'm going to say v, okay, for my integral here that I, on the left-hand side, u divided by u squared plus 75 over 4. I'm going to go ahead and say, let v equal, let's see if I can get a different color here to try to help out. I know it all looks the same. Okay, so we're going to let v equal, u squared plus 75 over 4. So we'll say dv equals 2u du. Okay, I don't have 2u, I only have u du. So I'm going to go ahead and divide both sides by 1/2. Okay, so now we're going to have 1/2 dv equals u du. So I can go ahead and approach this integral on the left-hand side. I'm going to go ahead and say that this is now negative 1/2, and I'm just moving over to v's. Okay, this is essentially like 1 over v dv. All right, so we'll come back and finish that off in a hot second. I also have this can of worms going on the right-hand side. I'm going to go ahead and factor out a 15 over 4 to start out with, and then we'll take a look at what we have. We have 1 over u squared. I also want to go ahead and see if I can try to rewrite 75 over 4 as something squared. Okay, it's a little tough, I know. So essentially, whatever we have, if we have 75 over 4, let's go ahead and try to think about what the square root of each of those are separately, because then I can say that, well, if I took the square root of them, I can rewrite it as that quantity squared. And that can get me a little closer to like the u squared plus a squared form that we typically will see. Okay, so square root of 75 is like 5 square root of 3, and the square root of 4 is 2. So even though it might not feel like normal, we could say that 75 over 4 is the same thing as the quantity 5 times the square root of 3 over 2 squared. This is where I feel like we might have some groaning. We haven't had it yet. Okay, so I'm going to go ahead and replace 75 over 4 with 5 times the square root of 3 over 2 squared. All right. Remember, I still have my left-hand side coming on down here, but you know, we have enough going on here. So I'm almost done actually with my integral, the second integral here, because I think it's time for me to actually bring this down. So I'll say 29 over 75 times the natural log of the absolute value of x minus 5. Now I'm ready to integrate 1 over v. That's also natural log. Okay, so I'm going to say minus 1/2 times the natural log. I'm also going to go ahead and swap back in what I had for v, which is u squared plus 75 over 4. And I still am going to have to go back and swap back in what I actually have for u eventually, but we'll just leave this like this for now. And now let's talk about what we have on the last integral. So we have 15 over 4. And again, believe it or not, this is just an arctangent because we do have it in the form u squared plus a squared. Whether or not we feel great about it, you know, could be, yeah. So u is just in the place of u, and then a is 5 times the square root of 3 divided by 2. Okay, so, you know, a little tough there, but that will just follow the normal arctangent. So just a little reminder of that in case we're not feeling like the most confident. But if we have like 1 over x squared plus a squared of times dx, this is the same thing as 1 over a times arctangent of x divided by a plus c. Okay, so we do have to divide by a, which is 5 times the square root of 3 over 2. But we have no fear because we can just find the reciprocal of that, which would be 2 over 5 square root of 3. Okay, and then we'll say times the arctangent of u divided by, again, same vibes, divided by a, which if I were to just follow the same thing I just did, I can go ahead and multiply by the reciprocal. Okay, I know it's excessive, plus c. Believe it or not, I'm almost done. I just need to go ahead and rewrite this in terms of x everywhere because I did that on my first integral, but not my second one. Okay, so we have the natural log of x minus 5. That one was surprisingly one of the kinder ones for us. Minus 1/2 times the natural log u was where we started. So it'd be x plus 5 halves squared. Let me fix that. Okay, so x plus 5 halves. Oh boy. Sorry, getting distracted. I got to go pick up my son, and I think I'm making up some, trying to squeeze it in the last minute. Always happens. Okay, so x plus 5 halves squared. Remember, that was like the x that we had originally picked in order to rewrite this whole can of worms and completing the square terms. Okay, plus 75 over 4. All right, minus, I can go ahead and simplify this. I have 15 over 4 times 2 divided by the square root of 3. So I can like simplify 15 and 5 is 3, and 4 and 2 can cancel out. So I would be left with 3 divided by 2 square root of 3. Arctangent, and I'm going to go ahead and again plug in 5 for u as x plus 5 halves. It's ugly. I told you it's kind of ugly. And keep the 5 square root of 3, and then say plus c. Okay, so believe it or not, that is what my answer is, which again is a little rude. I know it is. And even just like typing this in, we could rewrite this a bunch of different ways if we really wanted to. We could try to simplify some of these expressions a little more. We could go ahead and also distribute in the 29 over 75. We could do that. But if you also put it in just like we have this here, you should be totally fine. It's just a matter of really honestly, what do you think would be the least risky option at this point? Is would I kind of be able to type all this in correctly, or do I want to try to simplify it so it's less terms? It's up to you. Okay, so I hope this was helpful. Again, I know this was long. I just really wanted to make sure I worked through it completely. I'm going to add some timestamps, and hopefully they'll help me, but please keep me posted. Okay, thank you.